This is part 4 of a series on the support vector machine. In this video, we will implement a linear soft margin SVM. This video was produced in Korean and translated into English. My voice is AI-generated, text-to-speech. In the last video, we looked at the basic algorithm for the linear soft margin SVM. We looked at the slack variables to allow for misclassification and created an objective function for the linear soft margin SVM. We also explored the concept of hinge loss, explored optimization problem for that objective function, and created a decision function. In this video, we will implement a linear soft margin SVM by solving the quadratic programming for the dual function of the optimization problem. Let's implement this using the CVXOPT library. And let's also implement this using the scikit-learn's SVC and LinearSVC. And let's compare the results. The dual function of the soft margin SVM is as follows. This is equivalent to the dual function of the hard margin SVM. As we did in the hard margin SVM, we define this part as the matrix Hij. Then the matrix H can be expressed like this. This is an example where n, the number of data points, is 2. And this is element-wise multiplication. The Python code for calculating the matrix H is like this. Using the matrix H, the dual function can be expressed as follows. The objective function is the same as that of the hard margin SVM, but the constraints are different. This constraint has been added. Now we convert this problem into the standard form of QP and define each matrix. The problem of maximizing the dual function is equivalent to minimizing the negative dual function. And we also need this constraint obtained from the primal function. This is then an optimization problem with 2 inequality constraints and 1 equality constraint. Here, x corresponds to the lambda of our problem. And the matrix P corresponds to the matrix H in our problem. Matrices Q, A, and B can be defined as follows. And the matrices G and H can be defined like this. This part is the first inequality constraint. And this part is the second inequality constraint. Compared to the hard margin SVM, the matrices G and H are different. Now let's solve this optimization problem using the CVXOPT library and implement a linear soft margin SVM. The data we will use is like this. The class Y of the red data points is +1, and the class Y of the blue data points is -1. Because the red and blue are mixed, the two clusters cannot be completely separated by a single straight line. We need to approximate separation using the soft margin SVM. The constant C is set to 50. N is the number of training data points. And we define each matrix as defined on the previous page. We then use the CVXOPT solver's QP function to solve this problem. The lambdas, the optimal solution of the dual function, are like this. And we then use these lambdas to find W. The formula for finding W is as follows. Next, we use the support vectors to find B. Anything with the lambda greater than 0 is a support vector. We then use this formula and the support vectors to find B. For more information about this formula, please refer to the previous video. Visualize the training data points. Now that we have found W and B, we can create the decision boundary. The equation of the decision boundary is as follows. If we isolate x2, we have the following equation. Visualize the decision boundary. Next, let's find and visualize the slack variables, zeta. The decision function looks like this. And the formula for finding zeta is as follows. Next, let's visualize the positive and negative boundaries and support vectors. The norm of the W vector is calculated like this. And the unit vector of W is like this. And we calculate the half margin using this formula. If the decision boundary is shifted to the right by the half margin in parallel, this is the positive boundary. And if it is shifted to the left, this is the negative boundary. Now let's check the results. Successfully converged to the optimal solution. The results are as follows. The decision boundary looks like this, and the positive and negative boundaries are like this. Any data points with a small white circle within the red or blue circle are support vectors. They are mainly between the positive and negative boundaries. This data point that is misclassified and lies above the positive boundary is also a support vector. The lambdas of the support vectors are all greater than 0. And the slack variables are also all greater than 0. All data points that are correctly classified and fall outside the positive and negative boundaries have the slack variable of 0. These are perfectly classified data points like the hard margin SVM. This is the training process. In the prediction process, if a test data is at this location, we predict the class as +1 because it is above the decision boundary. When we feed this test data into the decision function, y hat returns a value greater than 0, thus predicting the class as a +1. If the test data is at this location, it is predicted to be class of -1. Let's run this code. The results are as follows. Next, let's classify this data using scikit-learn's SVC. The data we will use is the same as in the previous code. The constant C is also set to 50. Create an SVC model. For linear SVM, set the kernel argument to linear. We then fit this model to the training data. W and B can be found this way. Visualize the data points the same as the previous code. And visualize the decision boundary and the positive and negative boundaries. Then, find the slack variables and support vectors. The support vectors are contained in this variable of the SVC class. Finally, we visualize the slack variables and support vectors. The results are the same as using CVXOPT. Let's run this code. The results are as follows. This time we will classify this data using scikit-learn's LinearSVC. The data we will use is the same as in the previous code. Create a LinearSVC model. Set L2, i.e. ridge, as the penalty argument. This means this part in the objective function. And we set the hinge as the loss argument. This means this part in the objective function. C is set to 50, the same as the previous code. The loss can also be set to squared hinge like this. This uses zeta squared in the objective function. We then fit this model to the training data. We then find W and B and visualize the decision boundary in the same way as the previous code. In LinearSVC, there are no variables containing support vectors, so data points where the absolute value of y hat is between 0 and 1 are considered support vectors. Additionally, visually check for the hinge loss and squared hinge loss. The result of the hinge loss is like this. This is the hinge loss calculated only for the data points with positive 1 class. Is y hat, and the y-axis is the slack variable, zeta. This vertical line is the decision boundary, and this vertical line is the positive boundary. For correctly classified positive samples, the error zeta is 0, no matter how far to the right from the positive boundary they are. However, as they move further to the left, zeta increases. Hinge losses grow linearly, and squared hinge losses grow as a square like this. The visualization results look like this. This is almost identical to the results from the previous code. Only this data point is marked as non-support vector. This is because the absolute value of y hat is greater than 1. Let's run this code. The results are as follows. If you check these 3 results, they are all the same. Finally, let's see how the results change when C changes. The larger the C, the smaller the error, but also the smaller the margin. The smaller the C, the larger the margin, but also the larger the error. We cannot say which of these 3 is best. As the C changes, the most optimal C must be selected through cross-validation. So far, we have implemented a linear soft margin SVM using CVXOPT and scikit-learn's SVC and LinearSVC. In the next video, we will look at nonlinear SVM using the kernel function.